Hi, my name is Thomas Caswell, and thank you for watching my PyData Global 2020 talk. Today, I will be telling you about why you should be thinking about the separation of scales instead of the separation of concerns when you design your software. So first, a little bit about myself. I'm trained as a physicist, particularly an experimental soft condensed matter physicist. In grad school, I worked on a combination of jammed amorphous system, which are glass analogs, and I also worked on the fluid dynamics of the vapor layer below a Leidenfrost drop. Some of the data from that is shown below. What I learned in grad school is that the thing I'm most passionate about is building software to enable science and to build software for scientists to do better science more easily. And to that end, I'm now currently staff at Brookhaven National Lab at NSLS-II, where as part of a team, I maintain and develop tools for data acquisition, management, and analysis for use in the synchrotron community. I'm also the current project lead of Matplotlib. I'd like to start with acknowledgements of how I got here. First, I'd like to thank Michael Dropboom and the whole Matplotlib team for teaching me a lot of what I know and training me from a stereotypical cowboy physics grad student to someone who can at least produces usable software for others. I'd also like to thank Dan Allen and Ken Lauer, who are colleagues from Brookhaven National Lab, although Ken has since moved to Slack at Stanford. They were in the trenches with me as we built out a lot of the initial version of the software we maintain at NSLS-II, and we learned a lot along the way. And finally, I'd like to thank my wife Dora, who heard many early versions of this talk and provided valuable feedback. And without her support, I would not be able to do the amount of open source work that I do. So, in computers, we live in a very layered system. One might say an onion. So if we start peeling the layers back and start from, let's say I want to write some Python. That's text. That text gets parsed into a abstract syntax tree, which is eventually converted to bytecode, which is then run on the CPython virtual machine, which turns out that's a C program, which uses some C libraries and some Fortran libraries, particularly if you're using NumPy or Pandas or SciPy. But C programs are compiled to machine code. Machine code is what drives the digital circuits of the CPU. Digital circuits are made up out of transistors, but transistors are, when you look deep enough, just very carefully doped silicon. And for that silicon and the doping to behave as we need for it to be transistors, that relies on a lot of details of the crystal structure of the silicon and like the electronic structure of the electrons in that crystal, and the band gap. And there's a lot of very interesting physics there. And that whole thing is made up of atoms and electrons, and then atoms themselves are made up of protons, neutrons, quarks, gluons, and all those friends. And then at this point, we've run out of space on the slide and run up to the edge of physics understanding. But there's a $21 billion or 21 billion euro proposal to build the upgrade to LHC to try to go the next layer down. So this idea of layers is not new in computer science, right? This has been with us, almost from the beginning. To quote Dijkstra from a book he published in 1976, discussing what it means to do programming. And I will quote, "In other words, when asked to produce one or more results, it is usual to generalize the problem and to consider these results as specific instances of the wider class. But it is no good to just say everything is a special instance of something more general. If we want to follow such approach, we have two obligations. First, we have to be quite specific as to how we generalize. We have to choose our water class carefully and to define it explicitly, because our argument has to apply to that whole class. Second, we have to choose, invent if you wish, a generalization that is helpful to our purpose. I think this notion, so having received our marching orders, let's go ahead and build some layers. I think this notion of building layers and new abstractions applies to everyone who works with computers, right? This isn't just for people who do low-level libraries or people who do system-level stuff. If you do anything where you give the computer a list of instructions and then give that set of instructions a new name, it could be it typing any code at all in any form, using click and drag programming, configuring filters in your email client, putting a formula in Excel, any of that, you are creating an abstraction layer. And I'm not kidding. You've taken the tools you had available and built a new set of tools that is better suited to your needs and solves your problems better than the base tools you had. And that this process of building new layers on top of the layers we have is in some sense fundamental to what it is to be a developer. And as you go doing this, I'm going to propose a couple questions you should keep in mind during the design process. The first is you should think, what level is what you're working on targeting? If this is something, is this something that's targeted to be used directly by a human? And in that case, you probably should be very good about exception handling, that make sure it never makes it out, be very forgiving about the inputs, bake in as many assumptions as you need to make that tool as simple for the human to use as possible. On the other hand, if you're writing code that's going to be used someplace deeper in the stack and you expect to be extended by other code, then you probably want to have crankier interfaces that have stricter validation that will re-raise exceptions. Second question I think is critical to think about is, how does the information flow through your code? Right? What parts of your code need to know what information when, and how does that information move between the parts of your code? I think these two taken together, if you understand these, in my experience, if you get these right, the implementation implementation tends to fall out. Whereas if you don't have these right, you'll very quickly produce spaghetti code. And finally, at a somewhat more philosophical level, try to understand what the tool you're building is supposed to do, and what you can assume, and what you can assume, like what parts of it you want to leave free for the user to extend, and what parts do you want to lock down to just do for them. And this kind of will help define what the words of the vocabulary of this layer you're building to communicate with the computer is. And second, if you've been tasked with building a larger system that has many parts, I suggest you start with the simplest possible version of this. It's sometimes called Gall's law, the idea that all working big systems were derived from a working small system, and that when you're trying to prototype, build the simplest plausible version of all of your components that communicate the way you think they should, and make sure the system holds together. If you can start from the center and build out, it's very easy if you start from the outside, the user interface, and build in. There'll be decisions along the way that are arbitrary from the outside, but inside need to be coherent. Beware not to paint yourself into a corner. A question I always ask during design discussions is not can we do this extension, but do we see a path to adding this new feature in the future? And as long as you don't paint yourself into the corner, you're probably okay. And also remember, keep the end goal in mind, right? You don't want to build layers of abstraction purely for the sake of building layers of abstraction. You want to make sure they all are in service of achieving our goal. So at this point, we've all the advice I've said so far could really be summarized as do good things, which, while true, is not particularly helpful or actionable. So if we're going to dig into like what makes a good layer, what do we mean? To rephrase Dijkstra, we want to build tools that are easier to use than the layer below us that we're building on. And we also need to make sure they're flexible enough to solve more than one problem. Given that we're working in a layered system, we could consider looking at physics as a way to frame our thinking about how to think about complex layered systems. Physics has over a century of effort by a lot of people to understand like the layered complex system that is reality. But it's also what I'm trained in. And when you have a hammer, everything looks like a nail. So I came to this practice with that background. So that is the framing the rest of this talk will use to try to understand how to do software design. And for my fellow physicists, as a somewhat of a joke, I'm sure we can find a harmonic oscillator in here someplace. So a kind of a universal concept in physics is this notion of the separation of scales. And when I say scales here, I don't mean scales of like, in the sense of web scale, of just like lots of things. I mean, there's a separation of scales where things at bigger scales and smaller scales can be neglected when you're working at the scale of interest. This makes some intuitive sense in that if we wanted to compute the trajectory of kicking a soccer ball between you and your friend, we don't need to worry about the details of the quarks and gluons in the atoms of the molecules that make up the soccer ball, right? All of those effects can be averaged out, and we can consider the soccer ball as one thing, right? We have the soccer ball that gets kicked. Second, technically, Jupiter, away out the edge of the solar system, is applying a small gravitational pull to the soccer ball, but the effect of that is so small, it's not something we have to worry about. And in that sense, things at a bigger scale, we can neglect when we want to understand the ballistics of a soccer ball. Or put another way, this concept of separation of scales is how we take the complete problem of understanding the world and getting it down to a problem that can fit in our head, that we can reason about and is tractable. And when you do this, it is important to keep track of what simplifications and assumptions you've made, so that you know where what you've come up with is applicable or not. A really interesting, a classic video from the 1970s. It's about 9 or 10 minutes long. It starts from the scale of a picnic, and then zooms out to the scale of the observable universe, and then zooms down to the scale of subatomic particles, and showing you all the different scales that exist and how we can work at each of them separately. Kind of a concrete application of how we would use like such an effective theory to describe the scale of interest. So say we wanted to answer a question like, what is the pressure of 1/10 of a mole of gas in a 2-liter bottle at room temperature? If we know about atoms, we could compute the pressure by tracking every atom in the container, figuring out how often is the wall, and like measuring the pressure by how much force was applied. However, that requires several yottabytes of RAM, which is more than is, I think, available on Earth if you could get hold of every single computer. And like you're definitely not doing that by hand. It's just fundamentally intractable. On the other hand, we can answer this question using the ideal gas law, which is an effective theory of gas, which tells us that the pressure times the volume of a gas in a vessel is equal to the number of molecules times the constant R times the temperature in Kelvin, which in this case works out to 1.2 atmospheres. And then in this sense, the ideal gas law gives us a tool we can work with that is useful in its own right. We can use it to answer important questions like, is my propane tank strong enough to survive in the desert in the summer without exploding? And these effective theories can either be empirically discovered or derived from the scale below. And the fact that we can come at this from both sides is one of the ways in physics we use to make sure that our overall aggregate theories hold together and make sense. Another thing I've found in physics is that when you approach a problem, choosing the correct coordinate system can make all the difference. If we consider a circle, which in polar coordinates is a constant, so r equals 5, that's about as simple as you can get in terms of describing a curve. If you wanted to parameterize this, we can get x and y as a function of some parameter. We can trace out that curve as shown. But if you really wanted this as like a y as a function of x, we can solve that. It's multi-valued and imaginary in some places. It is not. It's a little weird. Like it's not a mathematicians will tell us it's not a true function because it's multi-valued. But you can make it work. However, if you're to look at something slightly more complicated, like what I'm calling a wobble, in polar coordinates, this is r is a function of theta with one trig function. That's not bad. If we wanted to get the x and y coordinates as a function of theta, we can also compute that parameterization. Again, there's more trig functions, but it's still fundamentally not that bad. However, solving y as a function of x is going to get messy. I've left it as a exercise to the reader if you want to crank through the algebra to get there. But I was going to say that it's looking at the graph. You can see there's some points where we've got one value as a function. There's one value for an x. Some places with 2, some places with 3, and a couple places with 4. And that this is just trying to describe this as y as a function of x is just not commensurate with the problem we have. And you find similar things in software. If you pick tools and languages which are well suited to your problem, it can be easy. If you're trying to use the wrong tool for the job, you'll feel like your tools are fighting. So just a quick word about how far we can push this analogy. Right? In physics, there is an objective reality. We don't really know what we have a pretty good handle on it, but we don't know what the right answer is, right? We can only discover it as we go. And really all of our descriptions of physics are effective theories because we don't know what the bottom is. And historically, really interesting science happens when we start to find failure modes in those effective theories. And if this is of interest to you, I highly recommend this book by Sabine Hassenfielder about the current state of theoretical physics. On the other hand, in computers, we, being humans at large, control almost all of these layers. But basically, until we get down to the physics of the transistor, all of those layers and all of these so-called effective theories between them are controlled and developed by humans. And that means we can build almost any effective theory or API, if you will, that you want. And we have much more freedom. But I still think that this framing of thinking about the scales and the interfaces between them is very helpful. Pulling this back to concrete terms quickly. My goal is to get the HTML of a web page. I can do this with 2 lines of Python, import request, request.get. And from as the user's point of view, this is very simple, it's 2 lines of Python. However, under the hood, there's a tremendous amount of work being done to make this happen, right? There's the DNS resolution to figure out what the IP address of the XKCD server is. Like once we know that, we set up a TCP connection, send some bits back and forth. Some of those bits are going to be the TLS handshake. Some of those bits are going to be the HTTP protocol, which is a non-trivial protocol. And then, if we're feeling particularly pedantic, we can go back to the third slide where we go through, the whole stack back down to back down to the quarks on both my machine and the server, and let alone, and we haven't even talked about the network stack yet. And these details are super important, right? Like if any of these things didn't work right, I wouldn't get my web page. But from my point of view as the user, I don't have to worry about them because they're averaged over and hidden from me. And this leads us to another, I think, a key idea that's come up again and again in computer science is this idea that constraints are one of the things that give us freedom and power, right? Because the ability to control something can very quickly turn into the burden of having to control it, right? And I think you can trace this idea back to Grace Hopper when she developed the first machine-independent programming languages. This idea is, I think, the core of Dijkstra's famous "Go to Considered Harmful" article, which it's only a page and a half. I recommend everyone read it. And there's more recent analogs of this. Nathaniel Smith's "Go Considered Harmful" blog post about structured concurrency, and Richard Hickey's Simple Made Easy talk about the design philosophy behind closure. So pushing on this idea of layers, right? If we accept there's a layer which has a different scale, and below that we don't know the details, that means we don't have to care about the details, and that means they can be switched out without us being affected. For example, if you're using copper wire or fiber optics or avian carriers to send your network stack, if your goal is to get a web page, it shouldn't matter to you how it's done. In the same way that if I want to send you a picture, if I choose to encode that as a PNG or a JPEG or a TIFF, those details matter, and someone somewhere has to take care of it. But the action of sending you a picture is independent of how I encode it. These ideas tend to come up in software engineering under the terms of like polymorphism and duck typing. And these ideas are what allow us to do dependency injection, right? If I write some code that says I'm going to take in something that looks like a Python dictionary, right, where I have keys and get item and dot items that do what they do on the Python dictionary, any object that matches those can be used, right? And as you start to lock these things down, this is where we start defining protocols and standards. And I think that a way to view this is whenever you have a standard or a protocol that you've defined, you're defining the edge of a scale, right? We're below that, you don't know the details, and above that, you can just use the interface. And in addition, I think in addition to convenience in programming, I think standards, particularly open standards, are critical for us when we try to tame the complexity that is computers. And one of the things they give us is the ability to work together, even if we don't know each other, or if we do know each other and don't like each other. Right? The fact that every web server on the planet speaks HTTP means that every company, you can talk to any company, and using any browser. Similarly, because there is a standard to email, you can have email services run by mutually hostile companies, but still communicate with each other via those tools. And one thing that has made me particularly happy is to see the convergence of power for peripherals converge onto USB. This is my box of accumulated power plugs for about 18 years of existing in tech. Much better if you just have it's all just USB. In particular, I think open standards are particularly important because that's what's going to protect us as a community from vendor lock-in and monopolies. So far we've been talking about what these layers and abstractions can do for you. I think it's worth saying what they can't do. In programming, complexity is conserved, right? There's some inherent amount of complexity in a problem that you can't get rid of, right? It's just inherent to the problem. You can say that if you're trying to model some real system, like in the real world, on a computer, the computer version is inherently as complex or more complex than the system you're modeling. And very much like the second law of thermodynamics, where you can only increase entropy in a closed system, you can only increase complexity. Not to say it's all lost. Like we can move complexity around. That's one of the things these layers let you do. Is you can take some of the complexity and hide it, but it's still there. It's not gone. It's just hidden. You've converted things that used to be options that you had to control to things that are now baked into the tool. As Maurice Moss from the IT crowd says, I will put this fire over here with the rest of the fire. And of course, you can always make it more complex, right? There's nothing preventing us from making it worse. Just can't make it better. And finally, for completeness, abstractions and layers are not all upside, right? They almost by definition, they add complexity to your code. They can slow you, they can reduce your performance because you're running things through interface. It's almost always going to be faster to go directly to the layer that your abstraction is talking to, rather than talking to it through the abstraction. As the Bitcoin miners have demonstrated, Python's usually slower than C, which is usually slower than the same computation on an FPGA, which is usually slower than the same computation in a custom ASIC, where the algorithm is encoded in the silicon. Of course, the trade-off is the wild increase in development time. Frequently, implementation details can leak through the interface. Frequently, in terms of performance, this is why random access into a Python deck can be much slower than the same into a Python list, and popping the first element off of a Python list can be much, much slower than popping the first element off of a deck. And then finally, if you use a tool to provide your abstraction and that tool is just not good, you now have two problems: the problem you had and the fact that your tool is broken. So one could ask, is there one true abstraction to rule them all? No, there's not. Just no. What tools do for us is that they're embedding assumptions about what needs to be done into themselves, which reduces their flexibility and generality, but makes them much more suited for that one task. So what's pictured here is a collection of specialty bike tools, which if you want to pull your cranks or remove your cassette, these are tools you need. Like, you could in principle do without it, but it's hard. I own these tools because I couldn't do it without them. However, these tools are almost useless for anything else because they have their assumptions so baked into them. In programming, the first tool that we work with is actually the language we work in, which is just a statement that may not be obvious at first. It may not be obvious on its face, but as soon as you hear it, it does seem obvious. And you're like, why did I think of that sense? And I recommend you watch these two talks, one by Ashley Williams, the other by Evan Czaplicki, talking about Rust, JavaScript, and async, and Elm respectively, which really push on the idea that a language is a tool, and that tool has goals and things it was designed to do, and you should use the language for problems that it is well fit for. Similarly, the functions and libraries and scripts are also tools, and what our job as developers is to use these tools to build the next tool that is better, that is even better suited for what we need. These tools help or control how you can express yourself to the computer, right? If you want to do the task of add 1 plus 1, the second thing you do after hello world, all the lines of code here do the same thing, right? They're all adding 1 to 1. However, they look wildly different, right? Based on the paradigm and the way of the language they're written in and like how it's structured. And this choice of spelling has consequences for what you can express easily, what problems are easy, what thoughts are easy to express in a language and what are hard. And it's also important to remember that none of these are the right or the correct spelling. The Python AST, which you mentioned at the beginning, is basically a declarative version of what the code you wrote here, having converted, printing x plus y as AST. And the Python virtual machine is a stack-based virtual machine. So Python bytecode is the stack version. But and what this comes to is that when we write code, we're really not writing code for the computer. We're writing code for other humans, right? The computer can take care of itself, right? You can go look at the obfuscated C competition or the Minify.js that you've almost certainly pulled from that's certainly pulled in your browser for any major web app these days, or any of the so-called esoteric languages, which technically run and are Turing complete, but are basically unreadable. And that the people you're writing for are frequently. So are your collaborators, and your most frequent collaborator is your future or past self, depending on where you want to look. I personally think past Tom is a jerk. 6 months ago, Tom has left me so many messes to clean up. It's terrible. And I hope I'm not the only person who has works in a shared code base. And every so often you read some code and you're like, this is terrible. Who wrote this? And you check get blame and you're like, oh, I wrote this. Other times your collaborators are your friends and coworkers, or sometimes they're strangers on the internet. But in all cases, our job as a developer is to use the tools we have and then produce new tools which simplify and structure the problem into something that we as humans can read and understand and reason about. So when we start thinking about the overall system, like an overall ecosystem, and all these layers, a way you can frame this, which is this is stolen from a talk Peter Wang gave, I think at SciPy several years ago. You can think of this as islands in the ocean, where the land above the sea level is the user application code, and everything below the sea level is the library code that supports it. And one way we can build this is by thinking of building volcanoes up over time, where you've got some broad base that's coming up, and just the peak sticks above water, and you've got this broad underwater mountain. A different way you could do this is you can imagine building so-called matchsticks, where you have your application and you build this very narrow stick that goes all the way down to the seafloor that solves your problem. And now if I want to build a second application, we can either have a second volcano or a second matchstick. And if all we're looking at is application code, these are about the same. However, if we want to now build a fourth island in between the first and second, if we have volcano code, we only have to build down as far as the nearest slope, which may be relatively close to the surface, depending on exactly where it is. On the other hand, in the matchstick case, we have to build all the way to the bottom again, because there's nothing's there. And that long term, our community of practice and open source is that we're building these shared volcanoes where everyone takes what's there, builds their thin layer on top, and leaves that for the next person. And just over time, we as a community build up. And with that, I'd like to thank you for your time. I'm looking forward to talking to all of you in the question and answer sessions. And this is just a final list of things that I read while preparing for this talk that I did not manage to cite somewhere else. Have a nice day.